Okay, welcome to another video. My name is Jesse. I am a VCE tutor or high school tutor in Melbourne. I am the founder of Simplified Study Tutoring, and I create a lot of videos now on YouTube, just kind of running through different skills based on some requests and things like that, as well as creating videos for my own students, breaking down a lot of different subjects across the VCE, including methods, further maths, all of the sciences, business, health and human development, legal studies, just about everything basically. And so someone said that they found the methods videos that I've done pretty helpful and asked if I could cover something from chemistry today. So what we're going to do is go through some electrochemistry questions from VCAA exams, and I'll kind of break down some of the theory behind it, some of the key principles that VCAA often assess. And then we'll also look at some much simpler ways to tackle the Section B questions from the exam as well. And so a bit of theory before we get started. If we just run through putting the two together, so we've got galvanic and electrolytic systems, we just need to know a few key facts. So first of all is just understanding the energy conversions. So galvanic goes chemical converted into electrical, whereas electrolytic is electrical into chemical. The second one is that galvanic is spontaneous, whereas so it doesn't require any energy inputs, it'll just happen on its own if the reaction is available. Electrolytic is non-spontaneous, which is why we need to put energy in, plug it into a battery or a wall unit or something like that. The next thing is red cat oxan. This one actually applies to both. So reduction at the cathode, oxidation at the anode. Does not matter which one you're doing, that will always apply. Usually I put that in the middle actually of this table, but I'll just leave it there for now. Then we've got, not oxidation, then we've got polarities. So here we've got the anode is negative and the cathode is positive. And then in this one, it's the complete reverse. So anode, cathode. So now it's the anode that will be the positive and the cathode will be the negative. In terms of reading the electrochemical series, what I would look for here is with galvanic, you want the two that are furthest apart. The bigger the energy gap, the more they want to actually react and more energy they want to give off, creating more chaos or entropy in the environment, which we know is a spontaneous process. Electrolytic, you want them to be as close together as possible, right? Not necessarily visually close together, but having the lowest difference between their two standard potentials, because that's the energy barrier that you have to pay in order to electrolyze something. So if the energy difference or the voltage difference is 1.5 volts, it means you have to put in at least 1.5 volts in order to actually get the electrolysis to happen. And then finally, I use a trick of left over right. And I think of it like this, left over right. And then for this one, it's the reverse. It's right over left, which again, think of like this. So the idea is that the reaction that can occur, so the available reaction in galvanic, is the one where reduction, so the forward reaction, is the higher on the left and the oxidation is lower on the right. If your left reactant is lower than your right side reactant, it means you have a non-spontaneous reaction and you will get no reaction in galvanic. If you put energy in, you can make that electrolyze. And the same thing for electrolytic. If you don't have a reactant on the right that is above a reactant on the left, then it means that you don't have an availability for an electrolytic reaction. Cool. All right, yeah, and that's pretty much a summary of all of the key skills that you would need for it. If you know those, that will usually get you through the bulk of the questions. Anything else might be more specific about a specific reactant and that kind of thing. All right, so this question here is taken from the 2017 exam in Section B, question 8. So if you did want to stop and kind of pull it up and work through it as we go, that's cool. So we've got fluorine gas, and I might zoom this in a little bit here. Fluorine gas is the most reactive of all non-metals. Anhydrous liquid hydrogen fluoride, HF, can be electrolyzed to produce F2 and hydrogen gases. Potassium fluoride, KF, is added to the liquid HF to increase electrical conductivity. The equation for the reaction is. So just in breaking down the reading of all of these things, they're trying to overwhelm you with a lot of different words. Really what you need is the reaction, and then the equation, and then the states of all of the different pieces. So you can see here that it's got liquid. Liquid means that it's not dissolved in solution. Same concept as when you see molten as well, means that water is not present. So if you've got aqueous solutions, then water is present. You've got to account for that as well. That could be getting electrolyzed. So, and the same thing with the galvanic as well. So F2 is used to make a range of chemicals, including sulfur hexafluoride, an excellent electrical insulator, and xenon difluoride, XeF2. Again, if you look around the question, there's really not anything talking about that at all. That's just giving you some context for its purpose, but it's not actually helpful to us in the question. The diagram below shows an electrolytic cell used to prepare fluorine gas. So we've got this whole setup here. I wouldn't necessarily really look at this too closely. I'll just move on, try to get straight to the questions. Liquid HF, like water, is an excellent solvent for ionic compounds in the same way that water molecules in an aqueous solution form ions. When KF is dissolved in HF, the K plus and fluoride ions form as they're written as blah, blah, blah with HF. So normally we say aqueous, but because we're using a hydrofluoric acid solvent, then we just can put that in the subscript there is what they're telling us. And this brings up a good point that often doesn't really get focused on in the course much, is whenever you've got a salt in solution, think of it as a source of ions rather than a solid salt itself. Try to think about things actually being able to separate or dissociate, and then how those ions can interact with other charged particles. So label the polarities of each electrode in the circles provided on the diagram above. This is a pretty classic type of question, asking you to label something from an electrical or electrochem setup, whether it's galvanic or electrolytic. Might be about the direction of electron flow, might be about the polarities of the electrodes, or labeling where the oxidation or reduction is happening, labeling the cathode and the anode and that kind of thing. So as long as you know one trick, so as long as you know that in galvanic, even though we're dealing with electrolytic, that the anode is going to be the negative, which is where oxidation occurs because it is the source of electrons, then we know that in electrolytic, the anode is going to flip polarity, it's going to now be positive. But the acronym REDCAT oxan applies across both setups. So for us, we're trying to label each of the polarities. I like the anode more than the cathode, so I'm just going to go, well, anode is where oxidation occurs. So I'm going to look for where oxidation is occurring. So if I go to the equation up the top here, I can get my states. So the H in the form of HF is in the 1+ state, and then the F negative is in the -1 state. It's then converting into solid, or not solid, into pure fluorine gas in state 0 and hydrogen gas in state 0 as well, because there's no polarity in that at all. And so therefore the hydrogen is decreasing, so that would be reduction, and then the fluorine is actually increasing from a -1 to a 0. So this is where our oxidation is occurring. So our oxidation will link to our anode. So I look to see where fluorine is getting produced, which is on this side. So I know this is my anode, like this, and so therefore I have oxidation occurring here, which means this is positive, and therefore that's negative, just like that, by default. So then write the equation for the half reaction occurring at the anode. So I've already done some of the work there. So now I know whenever I do half reactions, I always start with what I have and what I'm getting. So the first thing is started with F negative, and then leave some space to balance things. It's turning into fluorine gas like that. And I guess here I can put HF, because that's what it's dissolved in. Use that little notation. And now all I have to do is go, all right, so I need to add oxygen, or first I need to balance the fluorine. So I need 2 of them. Next up, I would add oxygen or add water to balance oxygen. There's none of that. Then I would add protons to balance hydrogen. There's none of that. And then finally, you add electrons to balance charge. And in this case, we've got 2 negatives over here, 0 over here, so I need to add 2 more negative electrons to this side. And that matches because it's oxidation, so it brings production of electrons. Then finally we have, or at least in this section, suggest why the diaphragm shown in the diagram above is important for the safe operation of the electrolytic cell. So this one, we do know that the diaphragm or the membrane is normally to complete circuits to have balancing of charge overall here. So it does also say the safe operation. So it's hinting for 1 mark that you're not really looking at the functionality of completing circuits or anything. The diaphragm or membrane is helping keep separate certain compounds. And we can see that what is being kept separate is not the fluorine, that seems to be on both sides, but the hydrogen, right? So the hydrogen is being kept away from it here. So what we're really trying to do is we've got hydrogen being produced, and we need to know as a fact that hydrogen is a highly volatile material, highly volatile gas, and so it generally is highly reactive with lots and lots of different things, including fluorine. They can actually interact very, very dramatically, and so we want to keep those two separate. If we didn't have this diaphragm in between, the fluorine gas that is dissolved could technically switch over here and then bubble with the bubbles of hydrogen gas here, and you could end up with an explosion. So it's all about keeping the hydrogen gas separated, given that it's volatile. So you could either get away with just simply saying hydrogen is volatile, or the safer answer would be to add in, and so the diaphragm keeps it separate, like that. So then we move along. I've got an electrochemical series over here as well. So explain why the carbon electrode cannot be replaced with an iron electrode. So whenever it's about choice of electrodes using inert things like carbon and platinum, this is about the relative reducing and oxidative strengths of different materials. So we're trying to have the fluorine, I'll just put some notes here, the fluorine we want to oxidize, and we want the protons, we want them to reduce like this. This is our goal here. So if we come over here and if we were to put in iron all of a sudden, the quickest way to do this is to highlight or circle what you have present. So we have fluorine present, or fluoride present. We also have protons present. The reason why I'm not going to circle this one is because that is with oxygen gas present as well. You can only include things that have all of the reactants available. So even though we have hydrogen or protons, we don't have oxygen gas available. It didn't say that oxygen was being bubbled through it, so we actually don't use that one. And I keep scanning. There's obviously no other fluoride, but there is hydrogen just here, right? And so currently they have a separation of this. And it's nice and simple. The separation or the standard potential here is going to be cathode minus anode, right? What we can also do is just look at the difference, 2.87 and 0. That has a difference of 2.87 volts. In electrolytic cells, you want that to be as small as possible because that is effectively the energy barrier that you have to overcome to electrolyze the system. If you put in iron, we'll go and find solid iron. I'll do this in another color, in fact. So where are we? Here we are. It's just down here. The problem with that is that now you've got another reaction that could happen that is a little bit closer here. So what would happen here is that you would end up with a galvanic spontaneous reaction occurring against the will of the system. So you can see that in galvanic we want left over right. And so this could actually now begin to reduce, but galvanically the iron would start oxidizing in preference to it. So that then would mean that would be easier than putting energy in to force the fluoride to reduce or to oxidize backwards. And so because iron here is lower down, this is going to be the reason why we use carbon inert electrodes. The explanation for that, though, we want to use the technical jargon. So remember that things that will preferentially oxidize are stronger reductants. So what is a reductant is itself oxidized and vice versa. So the explanation would be that Fe, and it's probably good to say solid, is a stronger reductant than fluoride, right? make sure you're using the name of the compound that is on the right side that would be oxidized to call it a reductant. So stronger reductants are lower on the right, stronger oxidants are higher on the left, right? So iron is a stronger reductant than fluoride, and so it would oxidize, and a good word to use in your answers is preferentially. Let me just spell that correctly. Preferentially, or in preference to the fluoride, and I would say under a galvanic reaction with the protons, like that. You wouldn't need to give an overall reaction or anything, and that would be it. It's pretty generous of them to do 3 marks. I would say that's really just 2 marks, but we'll take it. And then it says calculate the volume of fluorine gas measured at standard lab conditions that would be produced when a current of 1.5 amps is passed through the cell for 2 hours. So with these ones, what you want to do is 3 steps. So the first thing is you want to work out charge, right? Charge, which is, you can do Q is equal to IT, like that. But the other way to write it as well is that Q is equal to NF, and we can create 2 small equations here. We have currently time, and let's immediately convert that to seconds. So 2 times 60 minutes to an hour, 60 seconds to a minute, or 3,600 seconds to an hour. And so if we do that, 3,600, that'd be 7,200 seconds. Over here, this is our current, so this is our I, it's already in standard units. And SLC, 2 things we can think of here. That does mean the temperature is 298 Kelvin, and the pressure is 100 kilopascals. We could use the gas law, PV equals nRT. We could also simplify it and use the number from the data booklet that says that gases at SLC will occupy 24.8 litres per mole. So 1 mole is represented now by 24.8 litres. And we're going to use that. So step number 1, I'll get rid of this for the moment, is just going to be to calculate the charge in coulombs. So that's 1.5 times 7,200, like that. So this then would be, let's see, 10,800 coulombs. Step number 2 is then to convert that into a number of moles of electrons that must be passing. So if Q is equal to number of moles of electrons times Faraday's constant, the number of moles of electrons transferring is obviously charge divided by Faraday's constant. So 10,800 divided by, and 96,500 for that one there. And I'll just use my iPhone calculator because I'm going to be lazy about it. And let's see, 10,800 divided by 96,500. There we go, gives us 0.119171. So again, don't round intermediate numbers, make sure you carry them across. Then the third thing that we're going to do is we need to go to our half equation. So this was for fluorine, and that was fluoride reacting into fluorine. And we balanced this before, right? I'm going to leave out states because it's not really needed. We had this. So the number of moles of fluorine to the number of moles of electrons is 1 to 2 from the coefficients. So therefore the number of moles of fluorine gas is going to be 1/2 of the moles of electrons that we're transferring. So if we do that as well, we get 0.055955855. Lots of 5s in there. Like this, and then come up here. And then finally we can go, okay, so therefore the volume of fluorine gas is 0.055955855 times by 24.8. Because if 1 mole occupies 24.8 litres, then 0.05 mole should take up 0.05 of that volume. So we times that by 24.8, and we get 1.3878 litres. And then we check, so now we're going to go to significant figures. They've given us 2 sig figs here, 2 sig figs here. I'll assume, 3 significant figures it looks like they've gone to, and here it looks like they've gone to maybe 3. It's a bit ambiguous, so I might check everywhere else. No, actually it looks like they've just done 2 for us. Yeah, So this is really could be to 1, but they'll never do 1 sig fig. So I'll go with this one as giving us 2. So I'm going to say 1.4 litres. Like that is the volume produced. So then this question here, this is a fuel cells question. And so there's a little bit of kind of qualitative understanding of these. Submarines operate both on the surface and underwater. When operating underwater, the submarine acts as a closed system where there is no interaction with the atmosphere. So that means that whatever we have is all we have. So that means that there is no oxygen available or anything like that that's not being pumped in. There is some here, but it's not open to the air. Most types of submarines use both batteries and diesel engines to provide their energy requirements. A new type of submarine uses proton exchange membranes, or PEM, fuel cells, and diesel engines. Below is a diagram of the fuel cell. Blah, blah, blah. And again, I'm just going to move over this at the moment, come back to it in the question. State the function of the electrolyte in a fuel cell. Cool. So the electrolyte, it's the same thing as with a galvanic cell or anything else that's a bit more basic. It's there to balance the charge, right? So we can say it replaces the lost electrons at the anode, because it is acting as a galvanic cell, and balances the electrons gained in the reduction at the cathode. You could also say it completes the circuit, but that's a little bit basic for an exam mark. I'd probably give them as much detail as possible. You could even, if you wanted to, actually name what they may be. In this case, I don't think they've mentioned the electrolyte at all. They have not. So if you really wanted to be specific, you could say that instead of saying it, you could say the anions, like this, and cations. Balance the gain of negative charge to keep everything balanced. Write the balanced overall redox reaction that occurs in the fuel cell. So here, look to your reactants and your products. So you've got reactant of hydrogen gas and oxygen gas, and so therefore that should be forming water, right? So H2 plus O2 goes into water. I'm going to use the exact same method again. So just write my reactants, write my products. Now I'm going to balance it. Hydrogen's already balanced. Oxygen is not. Now that throws out my hydrogen. I need to balance that. And there we go. Everything's now balanced. And then I check, is this actually a redox? So the hydrogen here is in the 0 state. The oxygen's in the 0 state. Over here, the hydrogen is in the +1 state to balance out the -2 state. And I can see that my hydrogen has gone up, so it's oxidized, and my oxygen has gone down in state. So that's a reduction. So therefore I've got a pair, which means that my reaction is correct. Cool. And then I guess we could also put in as well, we should put in the states. I'm usually pretty lazy with those. Probably shouldn't be. Like this. And then water, which we'll say liquid. That one there. Give 2 safety considerations for the safe storage of hydrogen gas on a submarine. So it was weird that they had this in the same exam, but it is to do with the volatility of hydrogen, right? Volatility of hydrogen. Now maybe let's put an actual answer rather than just a note. So if I was to write that, it would be hydrogen gas is a highly volatile gas, and so storage must be secure and we'll say carefully located. Often hydrogen is stored away from people and away from townships and things like that to avoid risk. And then the other one as well is that hydrogen needs to be stored under pressure because it vaporizes very easily and occupies large volumes, which is not very efficient. Large volumes. Then we can say pressurized gas must be contained safely in, we'll say, appropriate vessels and regularly checked as well. And there we go. Cool. So then we have state 2 advantages of using the PEM fuel cell compared to a diesel engine when a submarine is underwater. So one thing to always go for, a surefire winner with why would we choose fuel cells? Key thing is fuel cells are much more efficient than any kind of fuel burning or combustion engine type system. So are much more, we'll say energy efficient as well. Energy efficient than the diesel engine. Actually, let's put that in context as well. So PEM fuel cells. And then another one is that it doesn't produce pollutants, right? So there's no carbon dioxide, monoxide, or anything like that. It doesn't produce pollutants. You could also argue as well that another one is that it's using readily available fuels. It's renewable, hydrogen and oxygen gas, that it's cheap or freely available for the most part. And you could also talk about the fact that most fuel cells operate very, very quietly because they're so efficient. You've got very little energy loss in noise and heat, and things like, or sound and heat and things like that. So you could argue that it's quieter as well. If you're talking about a submarine and like naval efforts, you don't exactly want a big giant submarine kind of like whirring through the water or whatever, and giving away the position. So it's also good from that perspective as well. Most submarines generate more hydrogen gas for their fuel cells when traveling on the surface. Explain how hydrogen could be generated. So this is a pretty tricky one. So all they've told us is that it's traveling on the surface. They said that when it's underneath the water, it's completely sealed off from the environment. And the system itself actually is completely sealed off. So you can't say that water or air or anything is getting into the fuel cell, but they did say it runs on both fuel cells and diesel engines. And we know that the key distinction between galvanic and electrolytic cells is that galvanic occurs spontaneously and converts chemical energy into electrical. Electrolytic is the reverse. It's non-spontaneous, and we spend energy to reverse a galvanic system and try to push the reactants in the non-spontaneous direction to convert electrical back into chemical energy again. So because we have energy from the source of the diesel engine, we could use the diesel engine to electrolyze something. And so if we're trying to make hydrogen gas, let's just go up here. We can go, okay, well, where can we see hydrogen gas being produced, and does it come from reasonably available reactants? So I can see, let's see, hydrogen gas, where were we, down in the middle here. Problem is that comes from protons. Didn't say anything that we had protons available. So that's a bit of a dead end. We can also see, where else? You can see hydrogen gas being produced here from water, right? We have water available, we're on the ocean, so that's a possibility. And then I think that's pretty much it. Can't remember where else hydrogen comes up. I think that's the only place. Yep, it's the only place. So that also just confirms the answer, that because we don't have acid available, then we have to do this. But in order to do that, it may cost energy. That may not be the spontaneous direction to, in this case, reduce the water. So we could use the energy from the diesel engine. So diesel engine could supply energy, show them that you know that energy needs to be supplied to electrolyze, and in this case that is going to be reduce the ocean water into hydrogen gas, like that. Right, so as long as you've mentioned electrolysis and that you've mentioned that there's supply that's needed and then what reactant is going to be electrolyzed, then you'll get your 2 marks there. All right, well, hopefully this is helpful, and hopefully this has kind of simplified and shrunk down this topic a little bit more. I know that when I was in year 12, a long time ago now, I always found this topic really, really tricky. There was a lot of 50-50 coin flipping, it felt like, but if you understand galvanic really well, you can often reverse your understanding to understand electrolytic. It's almost all the complete opposite. The only thing that stays the same is the red cat oxan thing in the middle there. Otherwise, it's all equivalent. If you did enjoy it, then please do like it. Do subscribe if you haven't already. And if there's something else you'd like to see, let me know, because exams are coming pretty close and I'm sure people have still got questions and concerns. I do cover most subjects, so chances are if you let me know what it is, I could probably do a video on it. I mainly cover the maths and the sciences, but some of the business and health subjects as well. All right, cool. I'll see you in the next one.